Hello and welcome back to another deep dive. Today we are opening up our chemistry textbooks again.
Yes, we are.
Specifically, we're focusing on Class 12 Chemistry, Unit 6. We are tackling the world of haloalkanes and halorines.
It is a very significant unit in organic chemistry. A lot of students find it challenging initially, but once you get the logic, it is actually quite systematic.
Right.
And it's very scoring if you understand the basics.
That is what we want to hear, scoring marks. And today we are zooming in on the very first step of that logic, classification.
The foundation.
Exactly. Now, before we start, I have a question for you. And for you listening, I want you to really try to visualize this. You might think that if a halogen atom like a bromine or a chlorine is surrounded by a big crowd of carbon atoms, it would be harder for it to react, right? Like it is stuck in a traffic jam at a busy junction.
That is a very natural assumption to make.
Yeah.
You assume the crowd, it blocks the reaction or makes it difficult for things to move.
Right. It seems like common sense. But here is the twist. Under certain conditions, specifically what we call the SN1 reaction, these crowded molecules actually react faster than the ones sitting out in the open.
That is correct. It is one of those counterintuitive things in chemistry that often confuses students.
So why does the crowded one win the race sometimes? Why is the traffic jam actually helpful in one specific scenario? That is what we are going to unpack today.
And the answer lies entirely in how we classify these molecules. It is all about understanding the structure.
This is our mission for this deep dive. We are looking at Section B of the source material regarding classification. And I want to be clear to everyone listening, especially if you are preparing for your board exams. This is not just about naming things for the sake of naming them.
Not at all.
This is about prediction. The source material says that once you know if a halocane is primary, secondary, or tertiary, you can predict its future.
Yes.
You immediately know if it will do an SN1 reaction or an SN2 reaction.
Yes. Think about the board exam paper. You see a reaction question. You might panic.
I probably would.
But if you use this classification, if you just check, is it primary or tertiary, you essentially unlock the marking scheme. You stop guessing and start knowing.
Wow.
It is the difference between writing a blank page and getting full marks for the mechanism.
So it's practically the secret code to predicting marks in organic chemistry, then?
Ideally, yes. If you get the classification wrong, you will likely get the mechanism wrong.
And that means?
And if you get the mechanism wrong, you lose the marks for the product. So this really is the foundation.
Okay, let us start at the very beginning. The zero-level explanation, as the notes call it. I want to make sure even a complete beginner can get this.
Yeah.
At the simplest level, what are we actually doing when we classify haloalkanes?
At the simplest level, classification is just organizing haloalkanes based on the carbon skeleton type, the one to which the halogen is attached. We are looking at the carbon atom that is holding the halogen, and we are asking a simple question. Who are your neighbors?
Who are your neighbors? I like that simplicity. The source mentions we also classify by the number of halogens like mono, dia, or trihaloalkanes.
Yes, that is another way.
But for today, let us focus on the carbon type. Primary, secondary, tertiary. Can you give us the anchor definition, the one we need to write in the exam?
Certainly. Let's take this slowly. A primary haloalkane, often written as 1 degree, has the halogen bonded to a carbon atom that is connected to only one other carbon atom.
Only one other carbon neighbor. Okay, got it.
Now, a secondary haloalkane, or 2 degree, has the halogen on a carbon connected to 2 other carbon atoms.
2 neighbors.
And finally, a tertiary haloalkane, or 3 degree, has the halogen on a carbon connected to 3 other carbon atoms.
I want to help the listener visualize this because definitions can fly out of your head during an exam.
That's true.
The source has a section called Imagine. So, listener, if you are safe to do so, close your eyes for a second. I want you to picture a long chain of carbon atoms. It's like a string of beads.
Yes. Visualize that chain, a simple chain.
Now, pick one specific bead, that's a carbon. Take away a hydrogen atom attached to it and snap on a halogen, let's say a bromine.
Okay.
Now, freeze that image. Do not look at the whole chain. Just zoom in only on that one carbon holding the bromine.
Correct. Focus your attention there. That's the key.
Now look at who is next door to that specific carbon. If that carbon is holding hands with only one other carbon bead, it is primary. If it is holding hands with 2 other carbon beads, it is secondary.
Yes.
And if it is connected to 3 other carbons, it is tertiary.
That is the perfect way to visualize it.
Yeah.
You are counting the direct carbon connections, nothing else.
There is a misunderstanding trigger mentioned in the source here. I feel like this catches a lot of students out.
Oh, yes. Very common.
Does the halogen itself change the classification? For example, is a chlorine compound different from a bromine compound in terms of being primary or secondary?
No, absolutely not. That is a very common confusion. Students sometimes think, oh, chlorine is different from bromine, so the class must be different.
But it's not.
No. The carbon type controls the classification. It does not matter if it is fluorine, chlorine, bromine, or iodine. You only look at the carbon skeleton the halogen is sitting on.
So do not look at the guest, look at the chair they were sitting on.
Precisely. The carbon determines the classification.
Okay, that clicks. Now, let us move to the analogies. The source material has some fantastic ways to visualize this.
Yes.
Because abstract molecules can be hard to keep in your head. The first one is called the delivery service.
Yes, this is the accessibility model. It helps explain why this classification matters for reaction speed, specifically for the SN2 reaction.
Right. And for SN2, we have this concept of a backside attack, right? The attacker has to come from behind.
Yes, and that is crucial. In an SN2 reaction, the attacker, the nucleophile, is a bit sneaky. It cannot attack from the front because the halogen is there guarding the front door.
It's blocking the way.
It has to come from the rear side, the back door.
Okay, so keep that in mind, listeners. The delivery person has to go to the back door. So let us break down the three types using this delivery analogy. What is a primary haloalkane in this picture?
So think of a primary halocane like a small independent house in a quiet colony.
Okay, an independent house. I can picture that.
The house is right there. It's very accessible. The delivery person, which is our nucleophile, can walk right up to the back door. There are no other big buildings blocking the way.
So in chemistry terms, what's happening?
In chemistry terms, the rear side of the carbon is open. The nucleophile can attack easily. This is why primary halocanes are great for SN2 reactions.
The delivery happens instantly.
Exactly.
Okay, that makes sense. What about secondary? 2 degree.
Secondary is like delivering a package to a row house. You know those houses that share walls?
Yes, where everyone is packed together in a line. It's a bit tighter.
Exactly. You have neighbors on both sides. It is still accessible, but it's a bit more crowded. The delivery person has to squeeze past a few parked scooters or cycles.
So it's moderately accessible?
It is. So the reaction is slower than primary, but still possible.
And finally, tertiary, the big one.
Tertiary is like trying to deliver a package to a flat in the middle of a massive, gated society during a festival.
Oh, okay.
You're completely surrounded by other towers. It is very crowded.
So crowded.
Very crowded. And remember, the delivery person has to get to the back. But in the tertiary structure, those 3 other carbon neighbors are big. They are physically standing around the central carbon. They are blocking the back door completely.
So the delivery person literally cannot reach the door.
He cannot.
Oh.
We call this steric hindrance. The delivery person simply cannot reach the reaction site.
Because the neighbors.
The neighbors, the other carbon atoms, are physically blocking the way.
That makes so much sense. So the more carbons attached to the central spot, the more crowded it is. And if it is crowded, the direct delivery or the SN2 reaction becomes
Impossible. Or very, very slow. That's the logic.
But this raises a question, which is in our section B2A. Why does this concept exist? Why did chemists invent this system of primary, secondary, and tertiary? Why can't we just mix chemicals and see what happens?
Well, we could, but science is about prediction. If we just mix things, it would be a guessing game. This classification system solves the prediction problem.
Can you give us a little history on that?
Sure. If we look back to the early days of organic chemistry, around the 1890s and 1920s, chemists like Walden and Ingold were studying these reactions.
Okay.
They found that just changing the carbon structure changed the reaction speed dramatically.
So they realized structure equals speed.
Yes. Without this classification, we cannot predict if a reaction will follow the SN1 path or the SN2 path. We would just be guessing.
I see.
This system gives us the rules to know what will happen before we even touch a test tube.
I love that. It turns chemistry from a guessing game into a logical puzzle.
It creates a framework for understanding.
Yeah.
Exactly.
Now, there is another mental image in the notes that I really like. It is called the person on the bench.
Oh, this is a very good one.
This one is really good for visualizing that term you used, steric hindrance.
Yes.
Okay, listener, if it is safe to do so, close your eyes again. I want you to imagine a carbon atom is a person sitting on a park bench. And this person has 4 arms.
A bit unusual, but stay with us.
One arm is holding the halogen. Let's call it X. Now let us look at the other arms.
If it is a primary 1-degree halocane.
Yeah.
The person is sitting at the very end of the bench.
Okay, at the corner seat. Easy to get to.
Exactly. One arm holds the halogen. The other side is just open space. It is bright. It is exposed. If someone wants to come and shake their hand, even from behind the bench, they can do it easily.
Because there is no one blocking them.
Precisely. Now, for secondary, 2 degrees, the person is sitting in the middle of the bench. There are neighbors on both sides. Let's say 2 big people sitting right next to them.
So the access is partially blocked.
Yes. You have to reach past the neighbors to get to them. It is a bit awkward,
And tertiary. This must be the huddle.
For tertiary, 3 degrees, imagine the person is not just on a bench, but surrounded by a circle of people. They are in the middle of a huddle, like a cricket team discussing strategy.
A huddle. That is a great image. I can see that clearly.
The halogen might be sticking out, but the person holding it, the central carbon, is trapped in what the notes call a human cage.
A human cage. So the nucleophile cannot reach in?
No. The nucleophile cannot reach in to grab the carbon or attack from the back. This visual explains steric hindrance perfectly. The crowd protects the center.
That is a very powerful image. It really explains why the tertiary ones struggle with that direct attack. It's not just hard, it's physically impossible.
Correct. The geometry forbids it.
Let us move to real life. We have talked about benches and delivery boys, but what about actual chemicals?
Yes, let's look at a lab phenomenon you can actually observe.
The source material gives us 1 bromopropane and 2 bromo-2-methylpropane.
Okay, nice chemical names. So 1 bromopropane is a primary haloalkane. The bromine is at the end of the chain.
Right.
2 bromo-2-methylpropane is tertiary. The bromine is right in the middle of a clump of carbons.
So if we do an SN2 reaction in the lab, what happens? What do we see?
With the primary one, the 1 bromopropane, the reaction is fast. If you are using a color indicator to track the reaction, you will see the color fade rapidly.
Why?
Because, like the independent house in the colony, the carbon is exposed. The nucleophile attacks, the bromine leaves, reaction done. Very quick.
And the tertiary one, what happens there?
If you try the exact same SN2 reaction conditions on the tertiary one, it will be very slow, or it might not happen at all.
Really?
Yes, you will be waiting and waiting.
Because of the crowd.
Because the crowd of carbon neighbors blocks the attack. It's a visible difference in the lab.
That is a clear difference. Now, what about technology? The notes mention Freon, or CFC-12.
Ah, yes, CFC-12. This is a classic example. This was used in old air conditioners and refrigerators for a long time.
And how does classification apply here?
Well, think about the structure. It is a fully halogenated carbon. It is extremely crowded with halogens. So the concept of crowding applies.
And that makes it stable?
Extremely stable. It is chemically inert. Because the carbon is so crowded and the bonds are strong, it does not react with anything inside the refrigerator.
Which is good for a fridge. You don't want your coolant reacting with the copper pipes.
Exactly. It was the perfect chemical for that job.
Yeah.
But as we learned later, this stability was a double-edged sword.
How so?
Because it was so stable, it didn't break down in the lower atmosphere like other chemicals do.
So it just floated up.
It drifted all the way up to the ozone layer intact. And that is where the damage happened.
I see. So the concept of crowding leads to inertness, explains why it was so good for fridges, but also why it became an environmental problem.
It all comes back to the structure.
Okay, we are getting towards the end of our deep dive, and this is the part where we need to get very practical. The exam-safe clarity lines.
These are the golden rules. If you remember these, you will avoid the silly mistakes that cost you marks.
Okay, I'll read the instruction, and you give us the clarity line. Ready?
Ready.
First one. A lot of students get confused counting hydrogens versus carbons. So how do we define a primary haloalkane without getting mixed up?
Here is the golden rule. A primary haloalkane has the halogen bonded to a carbon connected to exactly one other carbon.
And what should we not count?
Do not count the hydrogens. Ignore the hydrogens completely. Count the carbons. Always, always count the carbons.
Okay, clarity line number 2. Why does this all matter for SN2 reactions specifically?
The answer is geometry. SN2 attacks from the rear side. A tertiary carbon blocks this rear side with its carbon neighbors. That is steric crowding.
And a primary one.
A primary is wide open.
So 1 degree is open, 3 degrees is blocked.
For SN2, yes, that's the simple rule.
Clarity line number 3. We touched on this, but let's say it again. Does the halogen type matter for classification?
Do not confuse carbon type with halogen type. A primary bromide and a primary chloride are both primary. The carbon skeleton defines the class, not the halogen.
Got it. Okay, and the last one, this is the big one. The counterintuitive part we started with. We said 3 degrees is bad for SN2 because it's crowded, but what about SN1?
This is where the order reverses. And this is the most important concept for your exam. In SN1, the reaction doesn't happen in one step. The halogen leaves first.
And what does that create?
It creates a carbocation. Think of a carbocation as a carbon that has lost a bond. It has a positive charge. It is unstable. It is unhappy. It needs friends to support it.
It needs support. Okay.
Yes. And a tertiary carbocation has 3 carbon neighbors helping to stabilize that positive charge, like friends holding it up.
And a primary.
A primary carbocation has only one friend, so it is very unstable.
So let me get this straight. 3 degrees is bad for SN2 because it is crowded.
Yes, the crowd blocks the attack.
But 3 degrees is good for SN1 because those same neighbors support the carbocation.
You have nailed it. That is the crucial distinction. 3 degrees is crowded for SN2, but stable for SN1.
That is the line to remember, listeners. Write that down. 3 degrees is crowded for SN2, but stable for SN1.
If you remember that, you can solve almost any reactivity problem in this unit.
Okay, that actually clicks. I was always trying to memorize the list, but if I just think of the crowd, I don't have to memorize anything.
Exactly.
The crowd blocks the path for one, but supports the ion for the other.
Exactly. It is logical, not just a list of facts.
So let us recap what we have covered today in our short summary.
Okay, so we learned that classification is based on how many carbon neighbors the halogen-holding carbon has. 1, 2, or 3.
And we have the mental picture of the person on the bench.
Right. 1 degrees is at the end of the bench, open and accessible. 3 degrees is surrounded by a circle of people, crowded and protected.
And we have our golden rule regarding reactivity.
The most important one, 1 degree is open for SN2. 3 degrees is crowded for SN2, but great for SN1.
Next time you see a chemical structure on an exam paper or in your textbook, I want you to count the neighbors first.
Yes. Do not just stare at the halogen. Look at the carbon it is attached to. Count the neighbors. That is your key to solving the reaction.
It really is the secret code. Master classification and the rest of organic chemistry becomes much easier.
Absolutely. It is the foundation for everything else in Unit 6.
Thank you so much for breaking this down with us. It feels much less intimidating now.
My pleasure. Happy studying.
And to you listening, keep asking questions, keep visualizing those molecules, and we will catch you on the next deep dive. Goodbye.
Goodbye.